Okay, so the changes are only in the border when I'm subtracting a ZT and 1 plus 1 minus ZT when this one here for this equation minus this one here. The only difference is that I now have my alphas are different. Okay, so I'm going to have alpha 1 minus alpha 0. And here, this should read alpha 2, okay? Here, when I do it with the next sections, the last section, we have alpha 2 and alpha 1, okay? Which is this one here. So the important thing is that this, if we call this 1, 2, and 3, are stationary. Because there's white noise. I mean, it's a constant plus white noise. So that I have removed that polynomial trend by doing that. And then I can model the series as a whole. Now let's look at a different process. Let's assume that we'll have two sections, but we have a polynomial of order 2, a polynomial trend of order 2. So my series would be ZT would be alpha 0 plus beta 0 t plus gamma 0 t squared for t equals 1 through n1. And will be alpha 1 plus beta 1 t plus gamma 0 t squared, which is the same gamma 0, plus at, that's for t equal to n1 plus 1 through n. Okay. Then the second difference of ZT is, you can see it, let me write it down up here. I mean, the second difference of ZT is equal to 1 minus b squared applied to ZT, and that will be CT minus 2 CT minus 1 plus CT minus 2, correct? Now, if you use this expression here and replace the equations for CT in both sections of the data, then you'll see that when t equals 1 through n1 and n1 plus 3 to n, then the second difference will give you 2 gamma 0, because it's the same alpha, minus 2 gamma 0, it's the same gamma in both pieces of the data, right? So you'll have 2 gamma 0 plus the second difference of AT. I will not go through, it's just algebra here. I just have to replace this expression and replace, instead of ZT, I put this one here. Instead of ZT minus 1, I'll put this one, but with t minus 1, and so on. And you'll arrive at the second difference for CT is 2 gamma 0 plus the second difference of AT. Now, this, if there's doubt that we arrive to this thing, you should do it. I mean, you should do it in your out of class, just to make sure that you are understanding these different equations right. And then for the pieces, for the second difference, when t is equal to n1 plus 1, you get this expression for the second difference, okay? Which again, this is a constant. The important thing here is that this doesn't depend on t, and this is white noise. This is white noise. And the second difference for t, when t is equal to n sub 1 plus 2, again, this is just a constant. These are just the parameters, right? And this part here is a stationary time series. This is white noise, which is stationary. Okay. So by taking the appropriate number of differences, we have made the series stationary. And let me see here. Yeah, just do it as an exercise to make sure that you arrive to these the same equations, okay? Okay. Now, if you generalize this thing to a polynomial of order D, you'll arrive at something like this. You'll arrive at the difference of order D of ZT, provided that CT follows adaptive polynomial trends of order D, will be equal to some constant plus the difference of order D of AT, which is stationary. Okay, so we have made a series that non-stationary. This is the important thing, is that this thing is stationary. Okay. Now, and that's what that's what it says here. The difference of order D of ZT will have same characteristics as the difference of order D of AT, except for the level. The only thing that changes is the level. It's not going to be zero, but the level here is going to be delta factorial, D factorial times delta 0, plus this thing, which is stationary. So the slope is the intercept changes. It's not going to be zero, but it's stationary. The important thing is that the difference series, it is stationary. Okay. Now it can be shown that if you apply the difference operator to stationary time series, in this case AT, we obtain a stationary time series. I mentioned that result earlier, but it can be shown that if you take the difference of a stationary time series, difference of order 1, 2, 3, whatever, then this process is going to be stationary. The only thing that changes is, well, now the variance is going to be not sigma square, but it's still constant, okay? It's still constant variance. It is not sigma square, which is the variance of the original white noise, but it is it's also constant. It doesn't depend on T, okay? It's a factor of the number of differences, a factorial of the number of differences that we take. And that's an important result. If I have a stationary time series, if I take one difference, I'll have a stationary time series. You have two differences, I'll have a stationary time series. So regardless of how many differences I take from a stationary time series, the series is stationary. And that's, again, one risk that we have, because when we are trying to make a series stationary, there's a risk of over-differentiating, okay? Over-differencing. We may take more differences than required, since if we taking differences of a stationary time series, it's still stationary. But we'll see we'll see a way to avoid that problem. This is the consumer price index that we've seen before, from November 2013 through November 2016. As you can see, the series is not stationary. When I see a trend, that tells me right away that the series is not stationary. Now, if the series is not stationary, then the autocorrelation function will not die very fast. See, if you look at the autocorrelation function, we mentioned that last class, it's dying very, very slow. Okay, it's decreasing very slowly here. That tells me, if I look at the graph of the series, I can see it's not stationary. But also, if I can look at the ACF of the autocorrelation function, I can realize if the series is or not stationary. Okay, in this case, if the ACF doesn't die fast, then the series is not stationary. And that's the consumer price index for Mexico. Now let's look at the first difference. The first difference of the consumer price index, this is the graph of the first difference. And as you can see, now it is stationary, at least there is no trend anymore, okay? If I can draw a line here and I can observe that there is no trend in this series. I'll put a line here, and it's roughly, let's see, more or less like here. It's fluctuating around some constant value. So I do not have a trend. The series, I can say it looks like it's stationary. However, if you look at the autocorrelation function of the first difference of the consumer price index, you can observe here that it is not dying very fast. And you have a behavior here. Here, it looks like it's dying very fast, but it grows again. It starts dying very fast again, and it grows again and starts dying fast. This we will see later when we start talking about seasonal models, that this is a behavior that occurs with series that have some seasonal component. Okay, so the CPI, Consumer Price Index, is showing a seasonal component, a seasonal behavior, and something is happening every 12 months. So we'll see ways to model this thing. But at least from this, we see that the level of the series is constant, so I do not have a trend. However, we may observe also, if I try to draw lines here to look at the variance of the series, if I try to do that thing, let me take a line here, and I'm going to change colors here. See, look at this piece of the series, and I have this type of variability in the series. Here, I have different type of variability. In this piece, I have different type of variability. Then, and there appears to be some shift in level. And finally, I have this last piece, which has a lot more variability. Okay, so this series, we could say it's a stationary of first order stationary, let's say, because there's no trend. But it is not second order stationary because there is differences in the variances along the period of time. Okay. And we'll be dealing with this type of behavior because to model this series, we need to fix those things. We need to take care of non-stationarity and also of the fact that we have a seasonal component that occurs every 12 months. Okay.
So teacher, if we only looked at the autocorrelation function, we could say it wasn't stationary, or we can say it is, but with a seasonal component.
It is not stationary because if you look at the peaks here, the peaks are dying very slowly. So it is not stationary. It is first order stationary, but it's not stationary because there's a seasonal component that I haven't taken care of. Okay.
Okay.
And when you see behaviors that repeat, for example, in this case, you can see, imagine that you have history in the past. The most likely thing is that you would have something like this, a behavior like this, and you have the same behavior here. You have the same behavior here. So this is showing that you have a seasonal component. And we'll study those patterns when we look at seasonal time series.
Okay, perfect.
You're welcome. Okay, now this is the second difference. So here we saw, this is the first difference, okay? Now, if we didn't know that that we can model seasonality in different ways, we could think, well, it's not stationary because of what I mentioned. This is low. This is dying very slowly. Now, what if we take a second difference? If we take a second difference, the second difference looks pretty same essentially as the first difference, and I still have this behavior because the non-stationarity that I have in this series is due to the presence of a seasonal component that I'm not considering. Okay, so in this case, taking a second difference is not going to help because I will not get a stationary time series by taking a second difference. What that means is I do not have a second degree polynomial as a trend for the series. And let me go back to the series here. You can see that it looks like if I have a trend here, it's a first degree polynomial. So taking a second difference wouldn't make any sense. Okay. Now, what I was mentioning earlier is if I take differences of a stationary time series, then the series is stationary. So if I may over difference and still get a stationary time series. Now, when I take more differences than what I should, that makes model identification and estimation harder. It will be more difficult to identify the right model if we over difference. So it complicates model identification. It increases the variance of the series. This is a very important thing because that's what we're going to use to check. See, if I take more differences than required, the variance of the series is going to increase. See? And the other thing is, of course, we take two differences, we lose two observations. We take three differences, we lose three observations. So we are losing unnecessary observations. Okay. But this fact is what we're going to use to verify that we are not over differencing. We will compute the variance of the original series, the variance of the first difference, the variance of the second difference. And if the variance of the second difference is greater than the variance of the first difference, I already differentiated, over differenced. Okay, so I need to stick with the one difference. We'll start looking at that thing with very many examples. Okay, now the right number of differences, we can see that with the sample autocorrelation. Okay, what we expect to see is that the autocorrelations will die very fast. So after the first few lags, I say here 3 to 4, could be 5. After the first 3-4 lags, everything is zero. Everything, all the autocorrelations are zero, which did not happen in the series that we just saw. Okay. Now the consumer price index again, together with the first difference and the second difference. Okay, I repeated that graph here. This is the wrong graph. This is exactly the same graph as the second difference. We'll do it now in R. Okay, we'll do this example in R. Remember the random walk, which is CT equals ZT minus 1 plus AT. We said that the random walk is what? Is it stationary or not? Do you remember? We saw it last class or class before last.
They are stationary.
It is not stationary. The random walk is not stationary. The variance keeps increasing with time for random walk. Okay, remember that we saw that the variance.
But the difference is stationary. The difference the first difference is stationary, right?
The first difference, it is stationary, yeah. If I take here the first difference of a random walk, if I take the first difference now of CT, I will get CT minus 1, and that will be CT minus, and then CT minus 1 is CT minus 2, minus AT. Now I have my other AT. Let me erase this thing. I'll just do it simpler than that. First difference is CT, oops, CT minus 1. And then CT minus 1 is, from this equation, we see that that's equal to AT, which is stationary, right? It's white noise, it's stationary. The mean in the random walk doesn't change over time. Eventually, one of the characteristics of this random walk is that it will eventually return to 0. Okay, so the mean doesn't change over time. Expected value of CT is expected value of CT minus 1 plus 8. The expected value of AT, that's the expected value of CT minus 1. It's a constant. It's always the same. The variance depends on time. If you look at the variance of CT is the expected value of CT minus mu squared, and that's expected value of CT minus 1 plus AT, because that's what CT is, minus mu, all that squared. And if we compute now this thing, that'll be the expected value of CT minus 1 minus mu squared, plus the expected value of IT squared, plus 2 times the expected value of CT minus 1 minus mu times the expected value of AT. Now, this is what? This is the variance of CT minus 1. This is 0, right? Because the expected value of AT, this is 0. This is 0, so this term disappears. And I only have expected value of AT squared, and the expected value of AT squared is sigma squared. So the variance of ZT is variance of ZT minus 1 plus sigma squared. The variance of ZT minus 1 is the variance of ZT minus 2 plus sigma squared. And so that the variance of CT now becomes the variance of ZT minus 2 plus 2 times sigma squared, and so on. You can continue. And in general, the variance of CT will be the variance of ZT minus 1 plus n times sigma squared. Okay, so it will change. The variance will keep increasing with time. The variance of CT will increase with time. That's for a random walk. Okay. We're okay up to this point?
Yes, teacher.
Okay. Now the covariances in a random walk also depend on time. The covariance between CT and CT minus 1 is, by definition, the expected value of CT minus mu times CT minus 1 minus mu. Okay. Now, ZT minus mu is ZT minus 1 plus AT minus mu. I'm just replacing the fact that CT is equal to CT minus 1 plus AT, right? So that's why ZT minus 1 plus AT minus mu times CT minus 1 minus mu. And that's the expected value. I take ZT minus 1 minus mu squared, because I have ZT minus 1 minus mu here, and CT minus 1 minus mu here. So that's a CT minus 1 minus mu squared, plus AT times, this expected value is the whole thing, okay? Oh, that's right, it's right. These are the brackets. It's plus AT times CT minus 1 minus mu. And that's the variance. This thing exactly is the variance of CT minus 1. And we saw that the variance of CT minus 1 is varies with time, changes with time. But the first difference of CT is AT, which is white noise. So therefore, it is stationary. Okay. Now, in the case where the process random variables were mutually independent, then the autocorrelation of order K would be only 1 if again is equal to 0, and would be 0 otherwise, right? Because I remember we're assuming that and we'll be assuming throughout the class that AT being white noise has a normal distribution. Okay, so we're assuming the autocorrelation will be 0 for every K except for K equal to 0, which is going to be equal to 1. Okay, the autocorrelation. This is the first difference of 6 random walks. As you can see, taking the first difference, all the random walks fluctuate around 0 here, around a constant value. Okay, and this is the first difference of the 6 random walks. So you can see that the first difference is stationary, and it is actually a white noise. It's actually white noise. You can see that it has roughly constant variance, and it has mean 0. Okay, now let's go to the R script. I'm going to ask you to download to your computers a script that's called ST03 differences. And that is, let me show you where it is in Brightspace. Is T03, it's called differences and stationarity and estacionalidad. Okay, it's this script here. Please download that script. And once you're there, download the ST03 COVID script. And once you download this thing, run the package installation. Let me replace this thing by a reasonable. I'm setting the directory where I have my data. We're gonna need the IPC data, which I believe you already downloaded to your computers. It's the Inflación Mexico 1982 to 2016, and it's an Excel sheet. So
Ready.
okay. Okay, so as you can see, the file has only 2 columns. The first column is the date, and second one is the CPI, Consumer Price Index. Now, I'm going to convert this thing to a time series. I will no longer use to keep the date, so I use the same name as the data frame that I've read. I convert that data frame to a time series object with the data given by the IPC General. And I take this when the start date is January 1982, the end date is 2016. Okay. Now, if I look at the structure of IPC, it tells me that it's a time series object. Okay, that it starts in 1982, ends in 2017. I'm going to make the 2 graphs in the same panel. So I'm going to use the MF row, 2 rows, 1 column. I'm going to plot the CPI and the autocorrelation function, and that's the graph that you saw in the presentation. Okay, that's the graph that you saw in the presentation. Now, as you can see, it's not stationary. Then we take the first difference, and I'm going to look at, want to see how it looks like. So I compute the first difference with the difference of IPC, and then plot it together with its autocorrelation function. Oh, I forgot the, see, I put parameter row. And this is the graph. This is the same plot that you have in your data. Okay. And we can see that it's still not stationary. Now, we know that it's because of the seasonal component, but assuming we don't know that, let's take a second difference to see if we make it stationary. And if I make a second difference, I can do, but we saw it last time. We can say the first difference of I'm sorry, here it's wrong. Difference is equal to. Okay, the second difference is with difference is equal to. We saw last class that the first parameter in the diff function is the lags, and the second is how many difference we have to take. Okay, so I'm going to graph. That's the second difference. Okay, you can see now this is different from the one in the presentation because I put the wrong graph. I put the same graph in the presentation by mistake as the first difference, but anyway. So this is the fact, the autocorrelation function for the second difference. Now we see that we still have significant lags far away from the origin. In fact, we see that this one is significant. We see that the first one is significant. Here, if I look at this, this is well, this is like 0, though that's 1, right? That's okay. This is 1. I ignore that one, but I have a significant lag here, a significant lag here, another significant lag. Okay, so the ACL is still not dying. The autocorrelation function is not dying fast. So this means that this series is not stationary. Okay. Now we know because of what's happening here is that I may have a 6-month seasonality behavior, because this thing is happening at 6 months, 12 months, 18 months, and 24 months. So I may have seasonality behavior. We haven't looked into that thing, so let's just not bother with that now, because we haven't studied that type of behavior yet. Now let's check if we over differenced. Okay. Let's look at the standard deviation of IPC. Standard deviation is 40.52. What's the standard deviation of the first difference of IPC? It's 0.31. It decreased. Okay, so I'm not over differencing there yet. Now let's look at the standard deviation of the second difference. It's still lower than the first difference, so I'm still not over differencing up to the second difference there. Okay, however, the series is not stationary yet, because I have to induce a seasonal component. And we'll do that later when we talk about SARIMA models. Okay. And I'm going to graph the three charts, the IPC, the first difference, and the second difference, which I called IPC-D2. Let's make a correction here, okay? The second difference. And I'm putting printing the standard deviation in the title. So I'm saying I'm going to have 3 rows in one column, and I have here the series, the original series with its standard deviation, the first difference with its standard deviation, and the second difference with its standard deviation. So I have not over differenced yet, at least based on the criteria of the standard deviations. Okay, but we'll have to deal with several things here. we can observe that the first, when we took the first difference, we observed the differences in variance. So we need to fix that before we model, before we identify a model, okay? And this is just a random walk. That's I'm just generating here. I'm setting up a data frame, a matrix that will have all NAs. I'm setting up, I'm just reserving the space, 500 rows and 6 columns to generate the 6 random walks that you saw, okay? And I'm gonna generate normal random numbers with mean 0 and variance 1. I'm gonna generate 500 of those. That's why I put 500 rows and 6 columns, and I'm gonna do it 6 times. I already generated the random walks. Okay, I compare those objects as a time series. The structure, it tells me that it's a time series that has 6 elements, and the 6 of them are time series. Now I plot the time series, and that's what you saw in the presentation. That's a random walk, and if I take the difference, what I have is a stationary process, which is white noise. That's how the presentation you had on your presentation, on the PowerPoint, on the PDF. Okay, now let's look at another type of a structure for time series that has some advantages for dealing with time series. There's a file that I guess you haven't downloaded to your computers. Download the file that says, let me see what I'm reading it. There's a file, an Excel file called COVID-MEX_conf. This is confirmados y decesos de COVID. Okay, confirmados y decesos de COVID, and that's in Brightspace in the data sets. I put it here at the top, COVID Mexico. Oh, that's an image. I'm sorry. Let's see. I think I uploaded the picture and not download and not the data. Hold on. Let me load that data right away. Data sets. Here it is. Okay. Let me load this data set right away. Now I lost my Brightspace page. And I'm gonna load this file. It's COVID Mexico. And you'll find it at the end of the data sets. And just make it visible. Okay, please download this file. Okay. I don't know why it's taking that long. There's something wrong here. You're still, you're not able to see the file yet, right?
We can see it, but mine is also taking like a lot of time.
I don't know why.
Mine too.
It hasn't finished loading. Try again.
Mine already load also.
You already see it there?
Yes, yes, I can see it.
And you can download it?
Yes.
Okay, good. Now I can, it finished loading here. That's. Okay, so as you can see, there's a column that has the date and the number of confirmed cases and deaths. That's at the country level, okay? So with that, we're gonna have to load other packages. We're gonna load the zoo package, which is another package that is very useful to dealing with time series. And we're gonna load also the XCS package, okay? Let me know when you finish downloading these packages. And read the COVID file. Now this data is daily data, so it's better handled with the package called Zoo, which is a package to manipulate and model time series, and you can handle daily data or hourly data or whatever much better with the Zoo package. Okay. So that's why I'm loading this package Zoo. And once you read the data, let me know if you're ready.
Profe,
Yep.
es que no sé, o bueno, lo subió en PDF. ¿Cómo lo podemos pasar a Excel, a XLSX? O
It's an Excel file, right?
no, it's a PDF.
I download it as Excel.
Descárgalo con la nubecita. Ahí hay una
Ajá.
nubecita y te lo descarga como Excel.
Ah,
O sea,
ok.
no lo descargues directo del archivo. Arriba sale para que lo descargues bien.
Ah, muchísimas gracias, ¿eh?
See, aquí you see the three dots? You say download. It shows you here. Go in Excel or just save the file. You can open it with Excel and write it in the directory that you want. It's an XLSX file. Okay, so you can just save and
Thank you,
then put it in the directory, the right directory. Okay.
Thank you. Me apuro. Gracias.
Okay. Are you ready?
I am.
Okay. Well, as you can see here, the data has three columns, the number of confirmed cases and the deaths together with the date in the first column. So I'm gonna, to deal with zoo objects, the way to define the structure is a little bit different. So I set up the starting date and I read it from the file. Inicio is the first element in the column fecha, right? If you look at what inicio is, it's already in the format that the standard format for a date in R. And then I do the same thing with the fin, which is COVID-MEX fecha, and I take the last element, which is the one that corresponds to the length of the vector of the COVID fecha, right? And fin has the final date, which is that one there. Then we create, to handle these zoo objects, we create an index. That index is going to be, I'm calling it here INDS. Int S is a sequence that dates from inicio to the date final, to the end date by date. Okay. If I had hourly data, I would construct this index by saying it by hour. So it's very flexible to deal with daily data, with hourly data, and so on. If you look at the structure of ends, it tells me that it's a vector of dates. So I just have the vector of dates in that structure. Okay. Now I'm going to make the zoo series confirmados as an object zoo, putting down the data of COVID-MX confirmados, and using the INDS as the index for the dates. Okay, it's a vector of dates, and I do the dates the same way. Now I'm going to add. I'm going to plot the data. I'm going to plot here the confirmados, the confirmed cases. And that's, I'm going to plot now, these are the confirmed cases for the country. Okay. Then I'm going to add a vertical line that will show the date where that's the first time that López Obrador said that we have control, dominated the pandemic. It was on April 27th of 2020. So on that date, I'm going to put the red line because that's the date where he said that we had dominated the pandemic. And then I just add the text, línea roja, ya dominamos la pandemia. I just added that text here. And I'm going to plot now in the same panel, I'm going to plot the deaths. That's the deaths. I put the line also there. See, and that's a series, that's the COVID data. These are confirmed cases, and these are deaths. Okay, so as you can see, there's a clear pattern here, because as you know, every weekend, the number of reported confirmed cases decreases, as well as the number of deaths. Okay. So, but here you can see clearly how we got to a peak at the beginning of 21, then we went down, and now we're even a higher peak than what we were at the beginning of this year. Deaths have also gone up, but it's not at the same level that we were here. So yeah, you can see that thing. Now, let's look at how we manipulate some of this time series data, because this is going to be useful in many cases. See, the series starts on a Sunday. I put down here the first date. The inicio is March 1st of 2020, and that was a Sunday. And the end date is a Friday, is August 8th of 2021, August 20 of the 2021. Okay, so last day is a Friday. Now, last date is the maximum of COVID that fecha. And if I want to know which is the last day, I can use the function weekdays, which translates that date, the last day, into a day of the week. Okay. So it tells me that it is Friday. Okay, last day is Friday. So weekdays is a function that gives me the day of the week to which a certain date corresponds. That's okay, but in this case, it will be more useful to know the number of the day in the week, within the week. So I'm going to use this function as POSIX LT of last date W day. Last date, if I look at the structure of last date, you look at that structure, it is an POSIX CT object with this format, has year, month, and day. Okay. Now, if I just add the $sign W day, I get the number of day that that particular date corresponds. But now last day has a 5. Our numbers, the days in a week, starting from 0 in one, which is Sunday, and then 1 is Monday, 5 is Friday. Okay, that's going to be more useful because what I want to do is, since I know that the reporting goes down every end of the week, and the dates are, the figures are not reliable by the end of the week, what I want to do now is just take the data until the Saturday prior to the last day of information that I have. Okay, so the last day of information I have is on the August 20th, which is a Friday. So I would need to take the data on up to the previous Saturday, okay, to avoid the Sunday data, which I know it falls down. It's always underreported. So first I compute the Dias Sobra. I set it to 0. Now, what I say, because, and I set it here to 0 because if the last date is a Saturday, then I have no extra days. I don't have to remove any days from the data. So what I check here is if last day is not equal to 6, then Dias Sobra equal to last day plus 1. So if last day is different from 6, which is the case, in this case, last day is equal to 5, right? It's a Friday. Then Dias Sobra has the value last day plus 1. So if I look at what Dias Sobra is, I'm going to write it down here. Dias Sobra, it's 6. Okay, it's 6 because I have a Friday, and then to the next Saturday, I have one more day. Okay. Now, what I want to do is cut my data on the previous on the previous Saturday. So I now call it weekly.conf, confirmados, confirmed, and I'm gonna take the data. I'm gonna aggregate the data for per week. So I'm gonna take data from Sunday through Saturday. And that's the series that I'm going to grab now. And I'm going to manipulate now in live. So I say weekly conf, it's a weekly confirmed. I apply .weekly. It's a function that comes with the package 2, which is going to apply the function that I specify here per week. So it's going to take periods of 7 days, and it's going to add the values of the series. In this case, it's a confirmed series. So if I say this thing here, I say weekly.conf, and I'm going to apply weekly to the series confirmados from 1 to the length of confirmados minus Dias Sobra. Okay, because I'm removing the day so that I end up in a Saturday. Like that thing. I applied weekly. Now, if you look at this weekly.conf, weekly.conf is a zoo series. Again, it's a zoo object, but now it has weekly data. It doesn't have daily data. If I plot this data, and I do the same thing for the dev, okay? I apply the same function so that I aggregate weekly the data, and I plot this thing, and I have now the graph of the totals per week, which is less noisy than the actual confirmed by day because of that fluctuation we have. Okay, so in some sense it gives us more clarity as to the behavior of the series. Again, this is some of the advantages that we have with this package zoo. It comes very handy when we need to manipulate time series data, especially when we need to manipulate daily data or hourly data, okay? Because we can or if we have data that is not exactly equally spaced, and we have minute by minute data, for example, we can aggregate by hour, and we have the total per hour, or the same way I use the sum here, I could have used the average. Okay, I could use the mean of for each of the weeks. And if I instead of calculating the sum, I'm going to compute the mean, I just put the mean here, and it's going to apply by week. So this is a function that's very useful for manipulating time series data. Okay, and it's already 9:46. I'll stop it here. Let me